Hello and welcome. In this video, we're going to take a look at a particular type of series called a geometric series. Now, the reason why we're focusing on geometric series is because it has so many nice properties. It's relatively easy to spot a geometric series just by taking a look at sequential terms in that series. And if we can spot that, then it's easy to tell if a series is going to converge or diverge. And even more so, it's actually pretty easy to calculate what the sum is. So let's take a look. A geometric series is a form where we have AR to the n minus 1. And that's starting from n equals 1 going up to infinity. That means that our first term is simply just A. A is some constant. Now obviously A should not equal 0 here, otherwise it would be a pretty boring series. R, however, is the kind of important part of the geometric series. You'll notice that each new term in the series is obtained by just multiplying the preceding term by r. So we have a, which is just ar to the 0, and our second term is ar to the 1. Multiply that by r, we get the third term, ar squared. Multiply by r, and the fourth term is ar cubed. The nth term is ar to the n minus 1. So this makes a common ratio. We say R is this common ratio for the geometric series. Let's take a look at a couple examples of geometric series. Suppose we had 2 times 3 to the n minus 1. Well, for when n equals 1, our first term is simply going to be 2, and our second term will be multiplied by 3. So that'll get us 6. And our third term multiplies by 3 again, that gets us 18. And every new term is simply obtained by multiplying the previous term by 3 in this case. Now you can see that this is definitely a divergent series since I keep adding a larger and larger number and the terms themselves don't even go to 0. It might be possible though that each term could get sequentially smaller and it might be a convergent series. For example, let's say we have the series 1 over 2 to the n minus 1. Now, it may not look exactly like a geometric series, but we can always rearrange this and write that as 1/2, all to the power of n minus 1. And if we put a 1 in front, we can see that that's our first term, which is 1. And when n equals 2, we have a half, and every new term will be half the previous. Now, in a previous video, we've seen this particular series before. 1/2 plus 1/4 plus 1/8 plus 1/16. And we showed that that is convergent to 1. So this is a convergent geometric series with the sum 1 plus 1 equal to 2. Now let's take a look and see if there's a general way to determine if a geometric series is going to be convergent or not. Let's start off by looking at the general form of a geometric series. Let's start off with a special case first and get this out of the way. What happens if the ratio is simply just equal to 1? In that case, we just have the sum from n equals 1 to infinity of a. Now that's actually just a plus a plus a continuously. And if a is any non-zero number, eventually this is going to get infinitely large and this is divergent. With that special case out of the way, let's take a look at any other value for r not equal to 1. And in order to determine if this geometric series is convergent, we'll look at the partial sums. The nth partial sum, Sn, is equal to a plus ar squared and so on. But remember that the very last term, our nth term, would be ar to the n minus 1. Now we're going to do a little bit of a clever trick here. And what we'll do is we'll take this equation for the partial sum and we'll multiply the partial sum by one additional factor of r. When we multiply r, we're going to have to multiply each of these individual terms. Our first term, a, on the right-hand side, gets multiplied by r, and that becomes ar. Ar gets multiplied by r, and that becomes ar squared. Ar squared multiplied by r is ar cubed. Ar cubed multiplied by r is ar to the 4. But this is where I'm going to go ahead and say that we can understand the pattern already. Now, every additional term that I have skipped in the partial sum needs to be multiplied by r. And the second to last term, which I haven't written down, would be ar to the n minus 2. But if I multiply by r, then that power goes up by 1, and I would have ar to the n minus 1 as my second to last term multiplied by r. And my last term, ar to the n minus 1 multiplied by r, means the power goes up by 1, and I have ar to the n. Now, the clever trick comes in with subtracting Sn minus r times Sn. The nth partial sum minus r times the nth partial sum allows us to cancel out most of the terms of the partial sums. Ar minus ar squared minus ar squared, and you can see all of these terms cancel all the way up to ar to the n minus 1 minus ar to the n minus 1. Let's not forget that we are subtracting every one of these terms, so that's going to cause a lot of terms to cancel, but not everything. We have a minus ar to the n. Now, we can get an expression for the nth partial sum by solving this equation for Sn. We can factor the left-hand side, and we can factor the right-hand side. And I can divide both sides by 1 minus r because I already know that 1 minus r is not equal to 0. That's because I've already said that r is not equal to 1. That means that the nth partial sum, when r is not equal to 1, is given by a times 1 minus r to the n over 1 minus r. Now this alone is already a very useful formula. This allows us to add the first n terms in any geometric series where r is not equal to 1. Now what we're even more interested in here is knowing what makes a geometric series convergent. For that to happen, we need to have this limit of the partial sums exist. It needs to equal some value. And there's only one place where we see n. It's in the power. So r to the n is the only thing we really have to think about as to when this limit might exist. We would just need to make sure that r is a small number or close to 0. If r is a number larger than -1 but smaller than +1, then as we take that value to a larger and larger power, it's going to get infinitely small, getting closer to 0. So we say that this is convergent for the absolute value of r less than 1. If the absolute value of r is less than 1, or in other words, r is somewhere between -1 and +1, but not equal to either, then r to the n goes to 0 as n goes to infinity, and we end up with the limit as n goes to infinity of our partial sums equaling a over 1 minus r. And this is the sum of a convergent geometric series. For a not equal to 0, and r between -1 and +1, the geometric series converges to the sum a over 1 minus r. Now let's try a few examples and see if we can spot geometric series even if they aren't exactly in their standard forms, and we can calculate these sums. Now this first example appears to be written in sort of a standard form, ar to the n minus 1, and the sum from n equals 1 to infinity. And we can just take a look at what the different components here are. A is equal to 9 over 10. R is equal to 1 over 10. Because it's in standard form, it's very easy to see that this just simply converges. The first term is 9 over 10, and every sequential term is going to be 1/10 the previous value. Well, since R is between -1 and 1, we know that this converges, and its sum is equal to 9 over 10 divided by 1 minus 1/10. So that's 9/10 divided by 9/10, which is equal to 1. Now, if you stop and think about this for a moment, it's actually kind of an interesting result. 9/10 plus 9 100ths plus 9 1,000ths and so on equals 1. That means that 0.9 plus 0.09 plus 0.009 and so on equals 1, which is actually proving here that 0.9 repeating equals 1. Kind of an interesting result. Let's take a look at an example of a geometric series that is not written in standard form. Here we have the series 4 over 5 to the n, and we're taking the sum from n equals 1 to infinity. So it's a little disguised. It's not exactly looking anything like ar to the n minus 1 just yet. But we can use some rules of exponents here to try to simplify this first. First of all, let's take that 4 and remove that from the fraction and make that a constant multiple of 1 over 5 to the n, and then use a rule of exponents, and we can write that as 4 times 1 over 5 to the n. But even that is only in the form of ar to the n and not ar to the n minus 1. So what we can do is we can split factors. we'll split 1 over 5 all to the n into 1/5 times 1/5 to the n minus 1. And we can see that now our a is given as 4 over 5. Now we've got this in standard form, ar to the n minus 1, and we can see that this is also convergent since r is between -1 and +1. And that means we can now evaluate this, and we have a over 1 minus r, 4/5 over 4/5, and this sum also equals 1. Now, because this is a geometric series, we really only need to know what r is to find out if it converges. And it would suffice to be able to at least maybe see the first few terms and spot what r is by looking at the pattern. So we could even write this out and say that this sum is 4 over 5 plus 4 over 5 squared plus 4 over 5 cubed, and so on. And we can see that for each new term, we are simply multiplying by 1/5. You can spot that common ratio right away and say that this is definitely convergent. And our a is our first term, 4/5. And you can see that you really only need those two pieces of information to calculate the sum of a convergent geometric series. Now, we can even disguise this further. We have to be a little bit careful, again, with some algebra and rules of exponents. At first glance, this next series looks nothing like a geometric series. 4 to the power 3n times 2 to the 2 minus n. So that's actually a little more complicated formula to come up with each individual term. And rather than maybe actually writing out the series and writing out its first n terms, let's just see if we can simplify some exponents here. You'll notice that we have 4 to the 3n and 2 to the 2 minus n. We might actually be able to get a common base for those two exponentials. Well, that's 2 squared to the power 3n times 2 to the n minus 1, and we'll keep applying some more rules of exponents. That gives us 2 to the 6n times 2 to the 2 minus n, and we can add exponents. All right, well, now we're getting somewhere. We've got a single exponential function, and we can split that up into 2 to the 5n times 2 squared. Now let's see if we can finally get this into some sort of form of a times r to the n minus 1. That 2 squared is equal to 4, and splitting up 2 to the 5n, we can write that as 32 to the power n. And you can probably already see here that our ratio is 32. So this is definitely divergent, but one more step and we can turn this into ar to the n minus 1 if we want, just by taking that 32 to the n and splitting it up into 32 times 32 to the n minus 1. That gives us 128 times 32 to the n minus 1. So it's definitely divergent, but we know that a is equal to 128, and that's our first term, and every subsequent term is being multiplied by a ratio of 32. So this is divergent. Now in this last example, we have the sum from n equals 1 to infinity of 1 plus 5 to the n all over 3 to the n. And really the only way to see how this can be compared to some geometric series is to split up the fractions. And here we actually get to use one of the properties of sigma notation. If we have the sum of a plus b, then we can split that up into two separate sums. The sum of all of the a's and the sum of all the b's separately added together should get the same result by the associativity property of addition. So here we'll just say that this is simply two geometric series, the first of which is really just the same as 1 over 3 all to the power n, and so far that would be convergent, and another geometric series with 5 over 3 all to the power n, which shows us that r there is 5 over 3, and that's greater than 1, so that's divergent. And here are both those geometric series in their standard forms. Now, we have a convergent and divergent geometric series added together. Our convergent series, well, we could actually plug in a equals 1/3 and r equals 1/3, and we could figure out what that sum is, but that would be a finite number. However, in the other case, it's divergent, and we saw that when r is larger than 1, or if r is less than -1, then that limit of partial sums goes to infinity. So this would be a finite number plus an infinitely large sum, so overall it is divergent. Now, before we end the video, I'll just show you there is one other common form that we may see a geometric series in. With our standard form, ar to the n minus 1, this gives us the terms a plus ar squared and so on. And we see in that first term there that the power of r is simply 0. And actually, what we could do, instead of thinking about the first term here as being n equals 1, what if we were to instead start our indices starting at n equals 0? Well, then we could rewrite this sum as the sum from n equals 0 to infinity and simply just have ar to the power n. And those would be equivalent. And it's a very common debate as to whether or not we should index things starting at 1 or index things starting at 0. But here you can see, at least in the mathematics community, we agree that these are just equivalent here. It depends on which might be more convenient for the application. And this will, again, show up potentially in future videos with some applications about geometric series and convergence. So there we go. That gives you kind of a nice series to start off with. The geometric series, you can quickly determine if it's convergent or divergent. And if it's convergent, then we can evaluate the sum. That's not always going to be easy to do with other series. Even if we can determine that they converge, sometimes calculating the sums can be a massive amount of work, and it can take years or decades to try to even come up with an explicit sum for some of these series. So we'll stay tuned. Thanks for watching, and I'll see you in the next video.